right, so do you guys know what it means to be congruent? Two shapes are congruent if what's true about all their angles. All the angles are the same. Now, that only gets similar, but to be congruent, not only do all the angles have to be the same, but all the sides also have to be matched up. So congruent figures have all angles and all sides congruent. So that's what makes it an exact match. What's really nice about this is that when they name congruent figures in the book, in the textbook or any geometry worksheet or book, they name them, and we want you to do this as well, in corresponding parts order. Here's what I mean. Do you see the color coding here? A goes with E in this shape. See how they're actually a reflection of each other over a magic vertical line here. I think you guys did some of this back in 8th grade math, a little bit of reflections, translations, etc. So what's happening here is these two figures are congruent if you reflect A, B, C, D over E, F, G, H. So the A and E match, the B and F match, C and G match, D and H match, and any sideline. So what will happen is you can list all the corresponding congruent parts without even looking at the figure, because I know that AD in this figure is going to be congruent to EH in this one, because the letters are listed in a very specific order. Is that clear? So corresponding parts, you can list them all out. As a matter of fact, it's the first question in the homework, is here are two congruent shapes. What are all the corresponding parts? Well, you'd say A is congruent to E, B is congruent to F, C is congruent to G, D is congruent to H, AB is congruent to EF, BC is congruent to what over here? FG, and then CD is congruent to GH, and then you wrap back around again. AD is congruent to EH. And you don't even need the picture to do that, because they've written it in the order. The letters are in the order of the corresponding parts. Okay, so just make that clear. All right. So going on to the next, with that in mind, it says if HIJK is congruent to LMNO, and there's no picture here, what are the congruent corresponding parts? So we would say angle H is congruent to angle L, angle I is congruent to angle M, angle J is congruent to angle N, and angle K is congruent to angle O. Those are the four corresponding congruent angles. There's any shortcut on this, sorry. That's the way it goes. You list all four congruent corresponding angles, and then I would say HI is congruent to LM, and I would say IJ, the next two letters, are congruent to MN, the second and third letters in the other shape, and then JK is congruent to NO, and then HK, the first and last letters, are congruent to the first and last in the other one, L. So that's it. Now where we're headed with this is there's some shortcuts to proving, well, we're heading to proofs involving triangles, proving triangles are congruent. And for two triangles to be congruent, all 6 of their parts, 3 angles and 3 side lengths, have to be congruent. But what we'll learn is that you don't need all 6 corresponding parts to be congruent to prove that the triangles are congruent. You can actually prove they're congruent with just 2 or 3 out of the 6 corresponding parts being congruent. So you won't have to list all of them. So remember, a single arc here means congruent. The double arc means congruent. The single dash on here means those are congruent. By the way, what kind of translation would take A, B, C and match it up with EBC? You know which translation? Do you guys remember this from a couple of years ago? It is a translation. you know what this is? If I were to move this to rotation, yeah, that ends up matching them up. So these two are congruent because they both have a length of 4. Those two are congruent because they both have a length of 6. There's only one pair of angles that are not marked as congruent or labeled in such a way that we could visually see they're congruent, but they happen to be vertical angles here, right? So those are congruent by vertical angles. When it says justify your answer, that's all you need to say. Angle BCA is congruent to angle. Notice I'm starting at B, which is the double arc. I'm going to start at D on the other side of the congruent symbol because it's the double arc. So it'll go D, and then C, and then E. So I'm starting at B and D purposefully. They're both the double arc angle if you were to rotate and match them up. Okay. So by vertical angles. And then we do the same thing I just did up above here. Good times. We get to list all 6 corresponding congruent parts. So it was like this. Angle A is congruent to angle E. Angle B is congruent to angle D. And angle C is congruent to angle C, obviously, by vertical angles. And then we could even say, we probably should say BCA is congruent to DCA, because angle C, we don't know what angle we're talking about. We're going to learn this is called reflexive property if it's like that same angle equal to itself. And then the 3 sides that are congruent, we've got AB is congruent to ED, and we've got AC is congruent to DC, and then we have the last one is BC is congruent to, let's see, did I miss that? Okay, botched that. Sorry. Let's see, AC is actually congruent to EC. Sorry about that. AC is congruent to EC. And then BC is congruent to DC. So BC, I'm starting at the double arc here, going to C, and then starting at the double arc here and going towards C. So BC is congruent to DC. And AC is congruent to EC. So the 2 triangles are congruent. All of their corresponding parts are congruent. All right. This is called the third angles theorem here. Third angles theorem says that 2 angles of one triangle are congruent to 2 angles of another triangle, then the third angles are also congruent. That goes back to the idea of the sum of the 3 angles inside any triangle are 180. So if 2 angles in one triangle are equal to 2 angles in the other, the third one's already determined by that theorem. They have to add up to 180. So if you have like a 60 and 20 in this, and a 60 and 20 in this other triangle, those add up to 80. The angle that's left is 100, and it's the same in both. So that's the third angles theorem. I think it's pretty intuitive. So we're going to do a short little proof here. There's a whole bunch of given. So number 1 here, write all our given down. Angle A is congruent to angle D. Segment AE is congruent to segment DC. And I usually like to mark these as I go. Unfortunately, they've already marked these in here, but angle A is congruent to angle D. AE is congruent to DC. And the next one is EB is congruent to CB. So EB is right here, is congruent to CB. And as we go, we just keep adding another little hash mark. Each time you have a new pair of segments that are congruent, you just add another hash mark. And then BA is congruent to BD. So BA is congruent to BD. So we've got all the side lengths are congruent. That's all given. And then they gave us one set of angles that are congruent, and we've got to get the other two sets of angles congruent. Should have written just a little bit smaller here. So we're going to have a step 2, a step 3, and then a step 4. Because we've got to get angle ABE congruent to angle DBC. So angle ABE is congruent to angle DBC. That's because they are vertical angles. And I call this a bow tie. Kind of looks like a bow tie. It's an off-kilter bow tie, right? Anytime you have bow tie involved, it's usually use vertical angles because they come to a point right there where the knot of the bow tie would be. So when you see bow ties, think vertical angles are going to be in the proof. Okay, so vertical angles congruent, and then we'll use the new theorem that's just above this. If two angles in one triangle are congruent to two angles in another, then the third angles are congruent. So you can say angle E is congruent to angle C, and that's because if two angles of one triangle are congruent to two angles of another, the third angles are congruent. Move here. So if two angles of one triangle, they call it third angles theorem. I guess if you could remember that, I would know what you're talking about if you just label it as third angles theorem. You got to make sure that you know what you're talking about when you reference the third angles theorem. But here's what it means: if two angles in one triangle, so because these two angles up here, A and ABE, are congruent, and D is congruent to DBC, then the third angles, C and E, have to be congruent. And we will learn a shortcut for this in the next lesson, next Wednesday. You don't have to prove all 6 parts congruent for the triangles are congruent. You only need 3. In some cases 2 if it's a right triangle. So hang in there. Triangle AEB is congruent to triangle DCB because all their parts are congruent. So all their angles and all their sides are congruent, or all their parts are congruent. So they have to be congruent. Number 3 just says if two angles of one triangle are congruent to two angles of another, the third angles are congruent. And then number 4 says all their parts are congruent. So that makes the triangles congruent. If all 3 angles in one triangle are congruent to all 3 in the other, and all 3 sides in one are congruent to all 3 in the other, then they're congruent. All right, number 4 is an application of that third angles theorem. Just based on the markings here, I've got a 55 there, so that would make this a 55. I've got a 65 there, that makes this a 65. What must be true about all 3 angles inside a triangle? They do. They add up to 180. So you got 55 plus 65 plus 2x plus 30 has to equal 180. And then we're left with a little bit of algebra to do. So let's see here, we've got 120 plus 30 is 150 plus 2x equals 180. Subtract 150 from each side, so 2x equals 30. Divide by 2. X equals 15.
Can you also just find the angle on the left one?
You could, and then set them equal.
Yeah.
That worked too. So what would the angle on the left be here? That'd be a more direct use of the third angle standard. It's 60 degrees, yeah. So then here's the alternate method. Let's write it down. We got 60 equals 2x plus 30, and then you solve for x. So yeah, both would work. This in red is actually using the third angle theorem correctly. What I did in blue is using the fact that the sum of the interior angles of a triangle equal 180, which is used to prove the third angle theorem. If you look it up in the book on how they prove it using the third angle theorem. It's the same thing with this. This will show up on the test today, but this remote interior angles theorem, the idea that this outer angle out here is equal to the sum of these two, that comes from the sum of the interior angles of a triangle out to 180, but this idea that this thing is equal to the sum of these two over here. It shows up on today's test. I'll leave that picture up there for you.